So here are my notes on 2.7. I figured I'd project them because we're going to need to refer to some of these computational things as we do the problems. And I cannot remember them. So for your test, you might want to like have these special matrices written down somewhere. So computer graphics are made up of pixels, and coordinates of which pixels to show are stored in matrices. And that's how you program a computer to display graphics. You can manipulate the graphics, like stretch it, shrink it, rotate it, reflect it, by performing matrix transformations on the coordinate matrix of the image. So a translation, xy goes to x plus h comma y plus k. It can't be written as a 2x2 matrix transformation because, as we talked about in other classes, translations aren't linear transformations, right? So in order to make this work, we have to use homogeneous coordinates. We have to throw that 1 on the end. That's why we need it. Okay, so we're still working in a plane, right? X, where z is held fixed. So we're still in a plane. It's just not the xy plane. And it allows us to be able to produce translations via 3x3 matrix multiplication. So if you take this matrix where you just put ones on the diagonal, zeros everywhere except for the 2 entries in the third column, those are your translation by x and your x translation and your y translation. So if you just multiply these, just do the like flip and lay it on top, like you end up with x plus h in your first entry, right? 1 times x plus 0 times y plus h times 1. So you get x plus h, so that's your translation by x. And then your second entry, you have 0 times x plus 1 times y plus k times 1, which gives you y plus k, shifting you up and down. And then your last entry, it just keeps that a 1 constant, which is just always going to be a 1 because we're just working in the same plane. Okay, so this is something to have written down, right? This is how you do a translation in computer graphics. Okay, and then if you want to do a linear transformation, so any other kind of transformation that's not shifting, like a stretch or a shrink or a rotate, we use this kind of a matrix transformation. So you make this L where you put a 1 in the bottom left and then zeros up and over, sorry, the bottom right. And then A is the standard matrix for the linear transformation you're trying to create. Yeah. They're already there. Yep. Yep. Yeah, these are my notes on the reading. So they're on Moodle, and this is also in the book. All right, so A is the standard matrix for the linear transformation, which you can remember you find the standard matrix for a linear transformation by determining where the columns of the identity matrix go. Okay. So you figure out the standard matrix, and then you just sort of augment with these extra outer pieces. So when you're creating 2D graphics, we always use homogeneous coordinates and 3x3 matrix transformations to manipulate or move the image. And by analogy with the 2D case, if you want to do 3D, you have to go x, y, z, 1 for points in R3. Okay, so I'm going to leave perspective projections for, we'll talk about that after we do an example of the computer graphics thing. Okay, so here we've got a data matrix. 3 points, they're going to form a triangle. And I'm going to do some transformations on them, and then I'm going to show you how you can create those transformations using the matrix multiplication we just talked about. All right, so this is, these are all coordinates written vertically. So I'm writing all my data vertically. So 0, 1 is this point, then 0, 0, and 1, 0. So I have this triangle. All right, so now there's my data. Now I'm going to scale the x coordinate by 2. I'll do that in green. So my x coordinate for 0, 1, if you scale the 0 by 2, you still are at 0, 1, right? 0 times 2 is still 0. And 0, 0, multiply the 0 by 2, and you're still at 0, 0. But then 1, 0, if you scale the x-coordinate by 2, you land at 2, 0. So this green triangle is what I get when I scale the x-coordinates by 2. Green triangle. All right. Then rotate 90 degrees about the origin. So I'm going to take each of my 3 points, rotate them 90 degrees. So 0, 0 is going to be in the same place. Where does 0, 1 go if you rotate it 90 degrees about the origin? Negative 1, 0. Yep. And where does 2, 0 go? Move it 0, 2. Okay. So there's my blue triangle. Okay. And then one last transformation, and I'm going to translate everything right 3 and up 1. So each of my 3 points of my triangle are going to go right 3 and up 1. So I have 1, 2, 3, up 1, 1, 2, 3, up 1, and over 3, up 1. And my final triangle is right here. So I did three transformations. And my final data points, right, are 3, 3. Oops. I'm going to write these vertically because that's how our data matrix is going to hold all this data. 3, 3, 3, 1, and 2, 1. Okay. So I'm going to show you how the matrix multiplication that we just talked about can produce these points. Right, so our brains, it's pretty easy, like we can like visualize what we're talking about, go, oh, stretch it, rotate it, move it. But if you want to have a computer do this, you have to tell it a really specific computation. So this is what we're going to do. First, we make the data matrix with homogeneous coordinates. So we have 0, 1, 0, 0, and 1, 0. Those were our data. That was our data. But then we have to add these ones to make it homogeneous. So this is our data. And this is a little weird. We kind of work like right to left, where we do each transformation multiplied on the left of the data. So my next matrix is going to be the one that scales the x-axis. Scales the x-coordinates by 2. Okay, so anything that's not translating, that's not shifting, we create this L first, zeros with the 1 in the corner. And then what's left, there's 4 entries left. That should be the standard matrix of how you translate, of how you scale x by a factor of 2. And remember, standard matrices you find by figuring out where the columns of the identity go. Okay, so let's figure out how to do that. So I need to know what happens to 1, 0 and what happens to 0, 1. If you're scaling the x-coordinate by 2, 1, 0 becomes 2, 0. And 0, 1 becomes, nope, 0, 1. We're just scaling the x-coordinate by 2. So 0 times 2 is still 0, and we're not changing y. Those are the columns of your standard matrix. So those are the columns that go into the blank spaces of this scale x by 2 matrix. So I've got a 2, 0, and a 0, 1. I'm just going to switch colors so we don't get confused here. This matrix is going to be my rotation. Okay, so again, as long as you're not shifting, this is a linear transformation. So we set it up by making the L. And then we put in the standard matrix, what happens when you rotate 90 degrees about the origin. Okay, so I need to know what happens to 1, 0, and what happens to 0, 1. All right, if you rotate 90 degrees about the origin, 1, 0 goes to where? 0, 1. And where does 0, 1 go? So 0, 1 would be on the y-axis, rotate 90 degrees. Where is it going to land? Nope. Negative 1, 0. Yep. Should I draw a picture of that? Is that hard to see? Let's see. Yes. Yeah. Just like whenever you're dealing with trig, like about the origin, it means counterclockwise. So this guy goes to here, right? And then this guy rotate 90 degrees and it's going to land there. All right, so those are the new columns. Those are the columns of your standard matrix. So we're going to have 0, 1, and negative 1, 0. All right, and then my last matrix, the last thing I'm supposed to do is translate by 3, 1. So I have a 3 by 3 matrix. These are all 3 by 3 matrices. And the rule for the translate that's right 3 and up 1 was you put in 1s in the diagonal. There's 0s sort of everywhere except for those last 2 spots in the third column. And those are where you translate. Put 3, 1. Coming from this, yep. Yeah, I'm just following the rules that the book sets out. So it says, this is how you make a matrix that will transform, that will shift a point from xy to x plus h, y plus k. So I just copied this whole matrix. I put in 1s and 0s and the 3 and the 1, right? And then if you want to do any other kind of transformation besides a shift, you use this matrix. You put in this L of 0s with 1 in the corner. And then you put the standard matrix for that transformation in the remaining spot.
So HK equals 3, 1.
HK is 3, 1 in this case, yep. That's what works. That's just what works, yeah. So if we want to make it come out to have the points land where we want them, you just have to do it that way, yeah. All right, so let's just verify that when I do all of this multiplication, I'm going to land in the right place. I know where my points should land, right? They should land at 2, 1, 3, 3, and 3, 1, because I did it by hand. So this is a super long matrix multiplication to do by hand. So I'm just going to do it quick on the calculator. So I've got 4 matrices. This isn't even quick on a calculator because I have to do 4. Okay, so matrix, edit, 3 by 3. All right, so my first matrix, I'll do the translate matrix. 1, 0, 3, 0, 1, 1, 0, 0, 1. Go back into matrix, edit matrix B, 3 by 3. All right, and this is my rotate matrix, 0, negative 1, 0, 1, 0, 0, 0, 0, 1. Oops, 1. Okay, so that's matrix B. Then edit matrix C, 3 by 3. And this has to be 2, 0, 0, 0, 1, 0, and 0, 0, 1. And then I have to put in the data matrix, which will be matrix D. 3 by 3, and 0, 1, 1. That's right. And 0, 2, 0. Okay, 0, 0, 1, 1, 0, 0, 1, 1, 1. Okay, that is the last matrix.
So do you multiply them left to right?
Yeah, you could just write them in left to right. Like, so I want to do matrix A, oops, matrix A times matrix B times matrix C. Ah, shoot. All right, that's okay. Times matrix D. Do them all out. And we get 2, 1, 1, 3, 1, 1, and 3, 3, 1. Now remember, the ones in the bottom are just holding us in a plane, but 2, 1, 3, 1, 3, 3, those are the points I wanted to land on. When we did it by hand, that's what we got. Yeah, it is a lot of work, especially because like you feel like you can do that. We did it really fast by hand, but it was only 3 data points. When you're like writing a video game, right? There's like millions of data points. You can't do that for every single data point. You set something up like this. Yeah, and then your computer can do the multiplication like super fast.
And that's going on like there's CAD.
Yep. Mm-hmm.
So eventually you look at
Yes, yes. In fact, so what we're about to do, the next thing in this section is about how do you take a 3-dimensional object and put it in 2 dimensions, like for CAD or like maybe for chemistry, like you have a molecule and you want to be able to like represent it in 2 dimensions and move it around and look at it and stuff. So that's the projection, perspective projection. So perspective projections map each point in R3 to a point in the XY plane, which is a computer screen. So you do this by creating a line through the point XYZ, at some point on the 3-dimensional object, and the eye of the viewer, which is located on the Z-axis. So there's like me, then there's some 3-dimensional object that I'm looking at, and then behind that is a 2-dimensional plane I'm going to project it onto. So I'm looking at this thing and I draw a line from me right here through a point on my 3-dimensional object, and I write down where it hits the plane. And I can use similar triangles to determine where it's going to hit the plane. And we have a special matrix transformation for how to find the projection of any point with homogeneous coordinates x, y, z, 1. So let's highlight this because this is really useful. And then you have to also, you're going to get this, and to make the denominator, not denominator, the last entry 1, you divide everything by that last entry. All right, so I'm not going to derive for you where that matrix comes from, just like similar triangles, right? So you've got this picture that tells you how to map a point in 3D space onto the 2D plane, and you make lots of lots of similar triangles when you draw that picture, and then you derive by using the similar triangles, you get to derive this matrix.
What do we call that?
The perspective projection matrix. I don't know. All right, so let's do our second example here. I just have a triangle, like sort of the simplest picture possible. It's a triangle in 3D space, right? And I want to find its image under the perspective projection, where the eye of the viewer is at 0, 0, 10. So I'm at 0, 0, 10. There's this triangle in 3D space, and I want to project it into 2D space. Okay, so the projection matrix. So let's start with my data matrix. My data. So I have 7, 3, negative 5, and I have to add some ones. Whoops. 7, 3, negative 5, 1, and then 12, 8, 2, 1, 1, 2, 1, 1. All right, there's my data with some homogeneous coordinates, and then this is going to be my projection matrix. All right, so if I go back, let me just go back to what I highlighted, the projection matrix. It's just everything in it is just ones and zeros, and put them in the correct places. This is the only thing you have to calculate, negative 1 over d, where d is the distance of the viewer. So in our case, it's 10. Viewers at 0, 0, 10. Okay, so let's just fill in this. So I have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. This thing is the thing I have to calculate, negative 1 over d, in our case 10, and 0, 0, 0, 1. All right, so when you multiply those together, have your calculator do it. I did it already. It comes out to 7, 3, 0, 1.5, 12, 8, 0, 0.8, and 1, 2, 0, 0.9. So it doesn't quite help me because what I'm looking for is I'm looking for coordinates in the XY plane, right? I want two-dimensional coordinates. I started with 3D coordinates. I'm trying to project it into 2D space. So I now have 7, 3, and my third dimension is 0, but I have all these fourth dimension coordinates that are supposed to be 1s, right? They're just supposed to be placeholders of 1. So to make them 1s, I can just divide everything in that column by the last entry. Okay, so this is going to be divide by fourth entry. So 7 divided by 1.5 gives me 14 thirds. 3 divided by 1.5 is 2. 0 divided by 1.5 is still 0. And 1.5 divided by 1.5 is 1. Then you do the same thing for each of the other two columns. Divide each entry by the fourth entry. So 12 divided by 0.8 is 5. 8 divided by 0.8 is 10. 0 divided by 0.8 is 0, and 0.8 divided by 0.8 is 1. And then in the last one, divide each entry by 0.9. So I get 10 ninths, 20 ninths, 0, and 1. Now I have 3 two-dimensional coordinates. So my new two-dimensional coordinates are 14 thirds 2, 5, 10, and 10 ninths, 20 ninths. Questions?